All right, good day and welcome back to Everything Mathematics. And today we're going to continue the series we started yesterday on surds, and we're going to be looking at Rule 2 today. Yesterday we looked at Rule 1, and again, if you need a refresher, just go back to yesterday's video and you will see where we looked at Rule 1, which states that if you have the square root of a number, we could easily split that number into two factors of that number, and then, of course, we could find the square root of each factor in order to make a surd. And again, that's easier said than done. So basically, we had yesterday, if we have root A times B, we said that this is the same as the root of A multiplied by the root of B. And of course, A, B are here are just used here algebraically, but this will be represented by numbers. And what this rule allows us to do is basically find the square root of a factor of a bigger number. And sometimes it works out so nice that the two factors that we found or that we find can be the square root of those factors can be found. Sometimes it works out like that. Sometimes it's only one, sometimes it's both. But whatever we get, then we just multiply by each other, and basically we found the square root of that number. So yes, that's what we did yesterday. Today we want to focus on rule 2. So what does rule 2 say? Let's look at rule 2. Rule 2 states that if you have the square root of a rational, of a fraction, right? If you have the square root of an entire rational, the rule 2 allows you to segment it. So it's the same as the root of A divided by the root of B. Basically, that's what rule 2 allows us to do. So in other words, if you have a fraction under a square root sign, you can easily apply the laws of surds, or rule 2 here to be specific, you can separate the denominator and the denominator with their own radical, not radical, sorry, with their own root. So here, if we have the entire root of A over B, that can easily be represented as the root of A divided by the root of B. And again, from here, we could go back to rule 1. Sometimes A is such a number that we could split it and get a factor that can be square rooted, or in other words, we could find a factor that so happens to be a perfect square. So sometimes that happens when you do this step or when you reach this stage. And that's just the concept. Let's see if we could look at an example now. I see here I have a big number. Let's see if I could work it out. Right, so supposing we have, for example, the square root of 90 over 120. Good. I need more space. Let me do that on the other page. So we have the square root. Let me erase that. Okay, let's take that again. The square root of 90 over 120. So applying rule 2, that allows us to do this. The square root of 90 all divided by the square root of 120. And once we are in this stage, we can apply rule 1 to see if there are factors that could go into these numbers. As they are right now, I cannot see them. So let me just break it up and see if I could find a factor. So the top, this is the same as 30 times 3. Definitely 30 could break down again. And at the bottom, I could see 60 multiplied by 2. And that's just a start. We haven't finished yet. So let me go back to the top again. Or rather, let me put my working on this side. I'm trying to find a factor that's possible to rationalize, right? So let me look at 30 now. 30 would be the same as 6 times 5. And then what? 6 would be 2 times 3. Okay, so yes, I found one. So 6 would be 2 times 3. So this 3 and this 3 could be multiplied, and that leaves us with the 2 times the 5. Okay. So in other words, I could use what? That means there's a bigger number. Yes, 9. So I see a number here. So the best two factors to use on top here would be 9 times 3, right? Because 9 is a perfect square. And well, 10, there's no number that could break down 10 into, so that's that. Let's do the same thing for the bottom here. So we have 60, but we're looking for two numbers that could be rationalized. So again, I'm looking for 60. After 60, I could see again 30 times 2. Oh, so that 2 and that 2 could make 4, and 4 times this. Okay, so I found 1 already. And then from 30, I have 6 times 5. And from 5, I have 2 times 3 times 5. This is an interesting one. Okay, so I see 4. The best one I see here, oh shit, I can't erase like that. The best one I could see here is 4 times 30. It seems like that's the lowest I could go here. So here we have 4 multiplied by 30. That will give us 120, but 4 is a perfect number. Is there a higher number? How come there's no higher number? Yeah, when you go lower here, you're getting 6, then 2, then 3, then 5. Nah, I don't see it. So it's just here, it's just that. So here's, of course, this will in turn end up being root 9 multiplied by root 10, and that's all over root 4 multiplied by root 30. But 30 seems so big, almost as if you mean there's nothing else that could go into 30. I'll explore that a little just now. So root 9, that will be 3 root 10, and below we will have 2 root 30. But again, I'm questioning the 30. The 30 is so big. Let's see. So we started up here with the 30. So we had 6 times 5, yes. If we go to take another roll, we would have had, let me see, 15 times 2. But this is definitely a no-no again. No, I guess that's it. I guess 30 is the lowest it could go. But again, if it isn't, of course, please feel free in the comment section below to tell me. I don't know if I find 30 seems too big to remain as a under the root here. But quite frankly, I'm not seeing another factor that has a perfect square inside of 30. The best I could come up with is 3 times 10, but even 3 times 10, none of them are perfect. None of them are perfect square. So yeah, anyway. But yes, again, the essence, again, and that's what I wanted to get from all this, is that if we have the square root of an entire fraction, and that's rule 2 being applied here, we square root the top, we square root the bottom, and then we see how best we could write it as a surd. And as far as I'm concerned right now, this is the best I could have done it here. I'm not saying that's the absolute answer. I will play around with that root 30 and see. For all I know, that's as low as it could go. But for all I know, maybe I'm not seeing something else here. So let's do another example. So supposing we have now, let's say, root, I keep separating them, it's one whole thing after that. So supposing I have the square root of 27, and I want to divide that by 27 over 81. Of course, applying the rule, we know that this is the same as root 27 divided by root 81. And from here, we could see how we could rationalize, not rationalize, how best we could simplify. Well, guess what? I know that 81 is a perfect square. The square root of 81 is actually 9, because 9 times 9 will give us 81. So that makes our life downstairs a little easier. 27 is not the same. There's no number that we could multiply by itself to get 27. So here, let's see how best we could write it in a different style. Using back rule 1 here, I could see 27 being the same as 9 times 3. Yep, that should work. That should work. So that's the root of 9 multiplied by the root of 3. And that's all divided by 9. So ultimately, root 9 here would give us 3 multiplied by root 3, all divided by 9. Yep, that's it. And that's as low as you could go. Oh, no, I take that back. If you so wish, you could actually divide this 3 by this 9. Yes, that is possible. So the absolute lowest you could go in this question here would have been root 3 over 3. Yes, this would have been your absolute lowest, but I would think this is acceptable. I would think. But in maths, of course, you're taught that whenever you simplify to the lowest possible. And the lowest possible here would have been root 3 on 3. And if you're wondering how I got root 3 on 3 again, simple breaking down. So I use 3, 3 could go into itself 1, and 3 could go into 9 3 times. So in essence, there is a 1 in front of this 3, but as you know, the 1 is understood, so there's no need to put it there. And that's how we do that type. Oh, I don't know if I went across too fast. So that's how we, well, again, you're watching a video, so you could always pause and go back. But that's the habit. So accustomed teaching. Right. So let's go. Let's try another example. Let's see what I have here. Oh, somebody asked me an interesting question yesterday, and I want to address that sometimes. Yeah, that could work. So supposing I have something like the entire square root of 14 over 18, right? This is one that I was asked yesterday. So I just put this question to see if I could solve it. So the person asked me, what if there is no number that you could break down a number with when you're given a question? What do you do? And the answer is simple, just as when you're doing algebra. If you cannot go any further, then that's it. Your answer is right there. There's no need to try and make up magic. And I say that for the top. For example, if we look at the 40, so applying rule 2 here, this is the same thing as root 14 over root 18. Good. And the fact is that, so this is almost like the same scenario we had with 30. It's just that for me, it also had to be a little bit 30 because 30 is kind of big, right? But again, as I said, I would look into it. But there is no two numbers that you could multiply or get 14 and then also find a factor of it. For example, you could try, well, 14 times 1, of course. You could find 7 times 2. And after those two, there are no other two numbers. But 7 and 2, they're both also non-perfect squares. So then just splitting them doesn't matter. So at the end of the day, this one will stay like this, the 14, the root 14, because you just cannot go lower than that. So root 14 remain as it is, and there's just nothing you could do about that. On the bottom, on the other hand, we could have 18 is the same as 9 times 2. So ultimately, we have root 14 all over root 9 times root 2. So this is the same as root 14, and you divide that by 3 root 2. And for now, we will stop at this point. This will be the end for this here. But in rule 3, I will show you, which we'll be addressing tomorrow, God's willing. When you're dealing with rule 3, you realize that you have to, once you end up with a root at the bottom, you have to do what you call rationalizing. You have to rationalize. Simply meaning that you have to do something so that you don't end up as with a root, a square root on the denominator. As for why, to be honest, I've never questioned that. I wonder why. I don't know. I guess it's just a, how do you call it, a mathematical expectation, or, I say a convention. It's almost like when, like, so you have some people, even me, it's like if you have something like -8 plus 3, I personally don't like to see the -8 here. So I will quicker write something like 3 minus 8. I will prefer to do this. Not that anything is wrong with this. This and this is basically saying the same thing. But as a means of convention, I suppose that's what I do, maybe. So I'm not sure when it comes to having a square root at the bottom, it comes down to that, just convention, just somebody said that you have to do it. But yes, we don't leave a square root at the bottom. As a result, we rationalize, and that's what rule 3, tomorrow, God's willing, will be all about. Let's try one last example. One last example. What if I have the entire square root of 63 over, I see 10 here. Good. And again, in case you haven't noticed, it will be very helpful when you know your timetables when doing this. It saves you two things. First of all, it saves you time in finding what factors could go into a number. And two, it will help you to recognize certain number patterns a lot easier. So yes, when you know your tables, sad to say sometimes when we learn our tables in school, we learn it rote. So sometimes we can't associate. But yes, when you learn your timetables, you will be able to see certain numbers and know which numbers can make that number. So long as, of course, they are within the range of our timetable. But even if they're not, at the higher level maths, you have to be able to see patterns in all numbers, right? So this is the same as root 63 divided by root 10, applying rule 2. Remember, this video is all about rule 2. And this is the same as, we have to be able, and again, that's why I was emphasizing the timetable. here you have to be able to see that 63 is 9 times 7. And believe me when I say that's not the easiest thing to come up with. If you don't know your tables, I will admit to that, even me, right? And below root 10, there is no two factors that we could multiply to give us 10 in which we could square root one of them. So root 10 will remain root 10. The only two numbers that could give us 10 in this case would be 5 and 2, and 5 and 2 are not perfect squares. So no point in even heading there. At the top, we will end up with root 9 multiplied by root 7, and all that's divided by still root 10. And at the top now, root 9, that's the same thing as 3. Root 7 remain as it is. So that's your surd there. And all that's divided by root 10. And again, here we end up with a root as a denominator, with a square root and a denominator. And as I said, after tomorrow's rule, you would learn how to rationalize or learn rule 3, which shows us how to deal with denominators as a square root. So that will be the end of today's video. As always, again, feel free to share, like, and subscribe. And until the, subscribe if you haven't as yet. And until the next one, you take care.